Hello, welcome everyone. My name is Ryan Smith from Washington State University and ModX. This is ModX Network Voices. We're excited to have a guest on today, but before I do that, just like to have everyone say hello to Ivan Rupnik. Ivan, like to say hello.
Hello, everyone. Hi, Arash.
Hello, everyone. Hi, Ryan. Hi, Ivan.
And we are joined by Aresh Adel. Aresh is an assistant professor at the University of Michigan, and he runs a lab there. It's new. He'll talk about that. We're excited to have him. I've known Aresh for a while. He's interested in digital fabrication, but in particular, it's crossover with wood, a very historic and long-term material we have used in residential construction in the Western world and the United States in particular. Aresh did his PhD training at ETH in Zurich, Switzerland, and worked on the Dfab House, which we've talked about with Daniel Hall on this show. So Aresh, welcome, and please introduce yourself some more and tell us a little bit about your dissertation and also what you're currently working on. I think you have some things prepared as a presentation.
Great. First of all, I want to thank both of you for the invitation. It's a pleasure to come here and speak with you. So I'm gonna share my screen. I think you see great. So I titled the presentation Towards a New Mode of Architectural Production, and I'm gonna talk about mainly two things. First, my doctoral research. I will give a high-level overview of my doctoral research, and then I briefly talk about my laboratory at the University of Michigan, which we just launched in January. So it's about 2 months old right now, so it's very new. Yeah, as Ryan mentioned, my name is Aresh Adel, and I'm an assistant professor of architecture at the University of Michigan. I teach mainly in our Master of Digital and Material Technologies program, and I'm also heavily involved in our PhD program. Yes, and I'm going to go through some of the slides if that's okay. So the presentation, as I mentioned, is organized into two main sections, and briefly I go through over my doctoral research. I did I pursued my doctoral studies at ETH Zurich under the supervision of Professor Fabio Gramazio and Professor Matthias Kohler. And the title of my doctoral dissertation is Computational Design for Cooperative Robotic Assembly of Non-Standard Timber Frame Buildings. Yeah, I would like to start with this quote by Phil Bernstein that says, "Your next building won't be built, it will be manufactured." And this is from an article that was published in 2015. And he mentions several main reasons to support this code. The increasing use of digital technologies in the design and fabrication of building parts, which promotes a shift toward prefabrication, which we have seen strongly in the past few years. Economic factors such as high cost of skilled labor, speed of production, quality control, and efficiency, and also social and cultural factors such as the disappearing of craftsmanship in the building industry due to the instability of the market, for example, in 2008. As the material choice, I've focused my research on timber. And in my doctoral research, I specifically looked at modular timber frame construction as the offsite construction method. This slide illustrates the main steps of a typical construction process for multi-story modular timber frame buildings. As you can see in the slide, first walls and floors and ceiling panels are prefabricated individually. Then they're put together and then they're finished, transported to the construction site, put together, and then they're finished building. It's also important to note that what is the mainstream is that if digitally fabricated, digital chain mainly stops at the prefabrication of timber elements, parts, and their manual assembly. There are two main consequences for modular based on of modular prefabrication. The first one is that the amount of structural wood significantly increases compared to conventional on-site construction due to the dimensional constraints and the required stability of modules for transportation and lifting, which results in the duplication of interior structural walls where the building is divided horizontally, and the duplication of floor and ceiling frames where the modules are stacked on top of each other. A result of a comparison study by Ryan concludes that modular timber frame construction of a 4-story housing project in total requires 69.4% more wood compared to its conventional on-site construction. The second consequence is that modular timber frame construction is conventionally associated with standardized modules and usually result in cubic or cookie cutter buildings. This approach substantially limits formal typological and tectonic possibilities of modular timber frame construction. So to address this, then I asked the question, how this dominant paradigm can be challenged by an assembly-driven computational design method, which is coupled with robotic assembly techniques of bespoke timber frame models. In order to address these challenges, I defined three main research questions for my doctoral research. First, how to rethink the design, planning, and construction of modular timber frame buildings through an integrated computational design and robotic assembly process. Second, how can robotic assembly be effectively implemented in the design and fabrication of timber frame modules, and how can it expand the design space and add flexibility to the overall prefabrication process so we don't end up with a standard like cookie cutter buildings. And third, how to rethink modularization of timber frame building, capitalizing on an integrated computational design and robotic assembly process in order to minimize the required duplication of structural material, while at the same time add design flexibility. So these were the three main research questions of my doctoral research. To investigate these research questions, I proposed a new design and construction process illustrated in this figure. The proposed process targets off-site robotic assembly of bespoke timber frame modules here, coupling computational design, material processing, and cooperative robotic assembly. Then transportation, then finishing it, and then transportation of the modules to the construction site and putting them together to construct the building. What's important here is that this process is intentionally designed to shift the complexity of fabrication and assembly to the digitized environment of the robotic fabrication plant, while mounting remains simple and straightforward. And it's because you have a lot of control over the process. You have climatic control and sensing and different types of controls. But there is also a big challenge here. The proposed process requires a new fabrication-aware and assembly-driven computational design method, capable of integrating and satisfying an expanded set of interrelated functional, topological, geometric, and quantitative constraints, as shown in this slide, and facilitating seamless digital workflow for robotic assembly of non-standard modular timber frame buildings. This is because these new machines, these new construction processes require very specific data, and also come with very specific constraints that they need to be addressed in the design space in order for the building to be feasibly manufactured. The developed computational design method and workflow seamlessly linking generative design robotic assembly of bespoke timber frame modules, enables what's called the algorithmically generated modules being fabricated through a digital production chain and a just-in-time fabrication process as shown in this slide. The main step of this just-in-time fabrication process are a robot picking a raw timber element, cutting it in cooperation with a CNC saw, milling and drilling it, and then placing the element on the assembly stand spatially. And a human connects the timber element with the screw. So it also provides a good scenario for human machine or human robot collaboration. This process, as Ryan mentioned, I worked on the Dfab House, and this process was implemented in the design and prefabrication of the timber frame structure of the Dfab House. Dfab House is a 3-story building. The first floor of the Dfab House includes 3 novel concrete construction technology: mesh mold, smart dynamic casting, and smart slab. A 2-story timber frame building which sits on top of the smart slab is the case study of this research. The facade of the timber frame structure is a novel translucent facade system. This slide shows the prefabrication of the modules of this house, which took about 2.5 months. The modules sequentially were transported to the construction site and were assembled on site. The on-site assembly took about 1 day. And this is again to highlight that what we talked about, shifting the complexity all the way to the fabrication plant. And this is the photo of the Dfab House after its completion. I need to show this slide. This is the acknowledgement of the people who were involved in the project, because it was a highly interdisciplinary and collaborative project. Okay, that was just a brief overview of my doctoral research. Here I'm going to switch gears and briefly talk about a laboratory at the University of Michigan called AdR. We launched AdR in January 2021, so it's about 2 months old right now. AdR is an interdisciplinary laboratory for advanced research in architecture, computational design, and robotic construction. Our core research topics are fabrication-aware and assembly-driven computational design methods and tools, building a scale robotic timber assembly, and I put timber in brackets. That's our main focus, but we're also working with different materials. Then a big topic that we have just started and we're writing on a big grant is human-robot collaboration in the context of design and construction. How the future of construction will look like, and what are the opportunities and challenges for transferring this knowledge to the construction site and to the fabrication plants, construction sites in this. And the third, we also wrote a grant for this, is designed for assembly, disassembly, and reuse, circular economy, because the constraints of the material resources that we are facing right now. This is my last slide. This photo shows one of our cooperative robotics cells in action a few days ago. It's messy, yet it illustrates the work in progress. My students and assistants were developing a workflow and building and fabricating a timber sub-assembly. Thank you.
Thank you so much, Aresh. We'd love to have a little discussion here. I appreciate you presenting, and this provides a good background. Ivan, do you want to start off the questioning for us for Aresh?
Yeah, Aresh, really great presentation. I really appreciate it. And I really appreciated the clarity of the diagrams in terms of the control group of sort of timber frame, volumetric, modular, as compared to your investigation and the work at ETH. So maybe just to start a little bit, I think that the diagram you showed is quite typical in maybe European volumetric modular. Unfortunately, in the US, where we have a much larger industry and a lot more acceptance of offsite than we do in European countries, including Switzerland, in terms of market share, we don't have that kind of automation. So even the CNC pre-cutting process is almost a dream. And so maybe I just ask a little bit, because I think that's the goal of bringing you into you're bringing your really cutting edge research into this context and trying to have a conversation more within the industry at large. How do you see those kinds of persistent barriers to the adoption of automation? And is that something you're studying? Is it something you're interested in looking at? In addition to looking at really what is could be the cutting edge of the technological side of the investigation?
That's actually a very good question. And I was actually surprised when I moved back from Switzerland to the US and realized, oh, wow, the timber construction in Europe is, at least in Central Europe, is much more advanced in terms of the technology.
All of Europe. Anywhere you go, I promise. We've been everywhere. Sorry.
That's actually good. And one thing was that. The other thing is the quality of timber material and timber construction in Europe. I would say with the magnitude is much better and different. So this was a surprise, but also then we started looking, because one of our research principles, which I didn't talk about the research principle, is industry collaboration, is to work with industry. So when I moved back to the US, then I continued our collaboration with Aresh Adel, who was the industry partner for the PhD. And we invited them to Michigan, and we took our students there. Since this September, when I started my assistant professorship position, I've started looking at the supply chain in Michigan and starting making connections. Because if you don't think about the supply chain, if you don't think about how the materials are sourced, how they're transported, how the mills work, you really cannot have an impact. So we wrote a USDA Wood Innovation Grant. We're more on this grant. We're working with a few major players in Michigan and Midwest. One of them is a major sawmill, and I should say they're fairly automated, the sawmills that we're working with. Mm-hmm. Then we're working with a CLT manufacturer, probably one of the biggest, you guys know, Sterling. It's outside of Chicago. And then we're working with Chicago Council of Carpenters to bring them all under one umbrella, and then develop and understanding. And the whole grant was to understand what are the challenges right now and how we can advance what is the state of the art, or what is the current market, by like inserting some of our knowledge and transferring that from a community. So this has been one of our main focus. We're working on 2 NSF grants, and one of them, as I mentioned, is about human-robot collaboration, or the future of construction. And in this grant also, because we haven't submitted, so I cannot talk about the industry partners, but
we know how that
but we are working with a few of major construction firms, major players, construction, like largest construction firms. And again, understanding what are the constraints, understanding what are the barriers, like labor unions, and all the complexities that comes with like regulations, and then how we can transfer that, again, our research from. So this has been one of our main focus. I should also say I just started the laboratory, so we're fairly new, and we'll see in the next few years where we go.
I'm gonna pick up on that a little bit, Aresh. What Ivan was saying about the difference between the United States and Canada and what's going on in Europe. We're starting to see in our research and consulting work that there are more and more levels of computation and robotics being implemented in modular construction in particular. I'll point to 2 you're probably aware of in the media, and certainly our audiences, and that is the Autoval factory. House of Design is the robotics company out of Boise. And then Randek has developed a line, as you know, in the Modesto factory of Katera for conventional two-dimensional panels for apartments, simple walk-up apartments. So I kind of wanted to get your perspective on what you see happening and occurring there. And the question I think that people have is, what is the real benefit to doing conventional work with really, really sophisticated and capable robotic arms? Does that marriage make sense, given the fact that up until now, for probably 35, 40 years, we've been using two-dimensional nailers to put together panels, using that has been the machinery or the robotics. So see this transition happening. How much does that make sense, given the fact that the module actually hasn't changed all that much in that period of time? I know that was the focus of your PhD, but if you could comment on what's currently going on, or your perspective on what's currently going on with these more advanced modular manufacturers, that'd be great.
That's actually a very good question. And this was when I did the literature search in my PhD, there are similar companies in Europe, similar to Ketera, and that they're using robotic arms for the assembly of panelized construction, or planar elements. And what I realized was that they're looking at a robotic arm or this manufacturing as an automation, as to increase productivity, but still building or constructing or prefabricating what has been done since now. And the research question was that, okay, if you're working with a robotic arm, then it doesn't really care if you're assembling the panel 100 times or you're assembling 100 different panels. Because if you develop what we call the digital production chain, and the information flows from the design model all the way to the fabrication model or the fabrication process, then you can control it, you can mass customize. So I see a great potential there for mass customization, but this comes with other complexities. You cannot really work with conventional design methods, because conventional design methods are good with developing and designing what you call a one-off. As soon as you want to work with non-standard construction, and you want to have an effective design and construction process, you need to develop algorithmic processes that are capable of working with different parameters and different configuration, different layouts. So this has been one of, that's what I also mentioned, this has been one of our main focus in my lab, is to develop fabrication-aware computational design, to bring all that constraints that we see needs to be satisfied in manufacturing, and address them in the design space from the earliest stages of design, and provide tools so you can work with different customers, different manufacturers, different developers, and mass customize based on the program, based on the site, based on the requirements of the building, while the construction process is still as effective as it was a standard one-off, a standard process. So this, I see a huge potential there. Again, but it also has some serious challenges that needs to be addressed.
And maybe building upon that, I think Ryan and I also continue to teach in architecture schools, even though it's sometimes difficult. What you described, it's difficult still, even after 20 years of books like Refabricating Architecture, promising transformation and the role of the architect changing. It's still difficult to teach this other way of approaching it, which is in Europe and in industry in the US is really referred to as a kind of product platform, the design of product platforms as opposed to buildings. So we still find that even colleagues who have embraced digital fabrication in the US don't really understand what a product platform is, and still see it as a kind of a high-end way of doing custom work. Do you see, is that a challenge that you're also finding, and as you return from a very different educational context of DTH to which is a polytechnic system. Students are trained in a very disciplined way to approach conventional construction, in traditional construction. And in the US, we have retained a Beaux-Arts training, which really is form driven. For better or for worse, it works. It's worked for 100 years. Is that something that you see changing in terms of the culture of schools, but also the culture of research in schools?
That's actually a very good question. But there is a reason that I joined Michigan, because Michigan is known for digital fabrication and has been one of the leaders in the US. And we have an amazing fabrication facility and also amazing students. But I still see what you just mentioned, like this conventional way, what we call the phase-based approach to design, that you develop a form, you design, and then you go to like add details and then specify. In the program that I teach, we work with integrative computational design methods. That's what I mentioned, that you start working with different constraints and requirements from the beginning and implement tools, develop tools to design. It's very challenging because our architects are not used to work with code, with program. You know, we have a different medium. We were very visual. So this has been one of the challenges, one of the learnings for me as a teacher. But I see that I see a good potential if we start a little bit earlier, maybe in an undergrad. By the time the students are grad, they have like, because when they come from high school, they have very good mathematical backgrounds. They know what's a vector, what's.
Then they forget it all because we don't.
Exactly. Yes. So I think from an education perspective, I think we can integrate those into our curriculum.
That's great. And Aresh, maybe one more question, I think related to that, which is something we're finding is certainly what you're describing opens the potential for a number of futures for the built environment, really. On the front end of the design and fabrication process, as you described, there's a number of parameters that have to be taken into consideration. It sounds like your lab is trying to address that. There still is a big hurdle, certainly in industry, to overcome, which would be called the computational design process. One, there doesn't seem to be the skills out there necessary to do that. So even though we don't have labor availability, we're going to need to still train folks to go into that particular domain. And then the other is there seems to be a gap or a misunderstanding in industry that if I adopt these robotic tools and arms, guess what? It's going to save all of this time and effort. And that's not necessarily true on the front end, on the computational design side. So maybe you could just talk about that and inform our audience what is required to actually develop, these parameters, and what are you doing as a lab to sort of try to fill that gap, which is a real knowledge, skills, and also technology gap on the front end programming side before you even get to the fabrication floor?
That's again a very good question, also a very challenging question, because this is something that we're constantly thinking about. And as you mentioned, I see two categories. One is the gap in education, when we educate the future architects, the future construction. And there's also the gap currently in the industry, the profession that is already established for a long time. So I'm going to just talk about the education. So what we have done so far, as I mentioned, I teach in the Master of Science in Digital Material Technologies program. It's a highly specific program, and we train our students to be the leaders in this field. And so last year I taught the capstone studio, which is the research studio. And we have like different what we call engagement courses. And these engagement courses, one is for robotic, one is for material, one is for system, one is for coding. So the students really dive into like these tools and methods and way of thinking. As I mentioned, it's challenging at the beginning, but after like practicing it and doing it for a while, they adopt it. Something that I witnessed last year was because of the coronavirus. a lot of, or not a lot, but some big architecture were laying off architects or letting them go for a while because the projects were on pause. However, our students, they were getting like multiple offers. They were the ones from this program because they're trained, they're skilled. They go like to different manufacturers in East Coast, Midwest. So this, as you mentioned, I also see that there is a need for this and manufacture, and especially some of the manufacturers like Cornerstone and others in the US who are working with bespoke construction are seeing the value of hiring people who have these skills and then implementing that and integrating those skills into their process. I'm not sure if I completely answered your question.
No,
this is a topic that I can talk for a while. So.
No, absolutely. We appreciate your time, Aresh, and great presentation. We hope to have you back. And if anyone wants to reach out to Aresh, you can find him at the University of Michigan website. We'll also put on this his contact information in the video. You can see there on the screen. And thanks again, Aresh. Take care.
Thank you so much. Thank you. Have a great day.